Assalamualaikum and hi, we are from Group 1. We are here today to present our experiment report, which is Bernoulli's principle. Our group member have four group member, which is Lim Zi Hui and myself, Norainun Basyirah, Afiq Danial and Nurul Afifah.
This is our table of content. We have introduction, objective, theory, experiment setup, methodology, result, discussion, safety procedure, conclusion, and reference.
For the introduction, the Bernoulli experiment explores Bernoulli's principle, which describes the relationship between the pressure, velocity, and elevation of a fluid in motion. The experiment is fundamental in fluid dynamics and is widely used to understand and predict fluid behavior in various engineering and scientific applications. For the objective of our experiment is first to compare the measured and calculated fluid flow velocities in the ventral nozzle at a different point. Second, to investigate the static, total, and dynamic heat distribution along the ventral nozzle. Last one, to determine the flow coefficient at a different fluid flow rate.
In this slide, you can see that equation 1 is typical Bernoulli equations, and in venturimeter, we are measuring pressure in liquid, so it's equals to rho GH, and Z1 and Z2, you can see from the right top side is a venturimeter, and point 1 and point 2, because there is no height difference, so Z1 and Z2 is equals to 0. So we simplify our equations and we get equation 3. And the right hand side is the explanations about the symbol. P1, P is equals to pressure, H is equals to the height of water column, and W is the flow velocity, and rho is the density. And also we have H loss, which is the head loss. For this part, we are talking about volumetric flow rate. In theory, it is constant because you can see from the pictures, the venturimeter, the mass flow rate between point 1 and point 2 is equals the same. So for the formula, and then we can see the volumetric flow rate also equals to the same for the point 1 and point 2. So that's why we get constant here. For this part, showing how we going to get the theoretical velocity. You can see theoretical velocity is W1. So how do we calculate? So first of all, you can see the table there. We have a standardized reference velocity for each measuring point. We divide venturimeter in meter into 6 points, and then we have standardized reference velocity, and then we going to get each area divide by a reference AI, which is 338.6, and then we have equation 4, and then equation 5 is that when we already have the volumetric flow rate and also the area, so we can calculate W1, which is the theoretical velocity for equation 5. And then for equation 6, we are going to measuring the H dynamic. So we will measure H total and H static, which is the height in the manometer in the experiment. So when we measure H total minus H static, so we will get our H dynamic for equation 6. So why do we need H dynamic is we wanted to calculate velocity in experimentally. So we have the formula in equation 7. So W is equals to square root 2 multiplied by gravity multiplied by H dynamic. So we can get our experimental velocity. For this part, we are going to determine our flow coefficient. So for equation 8 is that the relationship between the volumetric and the flow coefficient kV. So we're going to rearrange it. So we get equation 9. So make kV as the main thing. So we simplify it and we get the finally equation is equals to volumetric divide by square root of gravity multiplied by um, difference in H. So the difference in H, we are going to get the difference between the inlet of the venturi, which is showing at the the pictures at the right side. So, and the narrowest diameter, which is the point number 3. So we're going to get their pressure difference, yeah, in this formula.
For the experiment setup, we have the white valve and the water inlet, ventrimeter, main switch, pump switch, black valve, 7 tube manometer, control outlet valve, measuring probe, volume water collect, and then the last one is a stopwatch.
So for the methodology part, number one is the main switch and pump is switched on. Number two, control outlet valve will be opened slowly until maximum level to remove air in the pipe. Number three, black cap valve on the top of the manometer will be opened slowly to release all bubble in the system, then close the black valve. Number four, control valve and pump will be closed. Number five, the white valve will be opened slowly until 80 to 100 millimeter. Number six, pump will be switched on again. Number seven, the control outlet valve will be opened slowly until level of manometer in P1 reach maximum and P3 at minimum level. Number eight, the reading in manometer for P static and P total for point P1, P2, P3, P4, P5, and P6 will be taken. Simultaneously, the volume of water collected at the tank will be recorded for each point with the time. Number 9, the outlet valve will be adjusted by reducing the flow to determine another reading. Number 10, step 7 until 9 will be repeated.
This is the result that we gain in our experiment, and this is our experiment data.
So, for the discussion part, number 1 is asking us to calculate the fluid flow velocity in the venturi nozzle at different points. So, using the formula of W equals to square root 2 times G times H dynamic, we can get each of the velocity at each point, which is at P1, P2, P3, P4, P5, and P6.
Discussion 2. Calculate and discuss the static, total and dynamic heads distribution along the venturi nozzle. Below are the graph and table for static, total and dynamic head for 4 liter and 6 liter. As we can see that the static head for both 4 liter and 6 liter is the highest at P1 and the lowest at P3. And the total head is the highest at P1 and lowest at P, and it started decreasing at P3 and then gradually increasing. Other than that, we can see that the dynamic head for 4 liter is larger than the dynamic head for 6 liter. This is because the difference between the static head and total head for 4 liter is greater than the difference of the static head and total head for the 6 liter.
For calculating, we get flow coefficient and different fluid flow rate. So we use volumetric flow rate that we gain from our experiment, and then we calculate the H difference, and then we multiply with gravity, square root it, and then we take the volumetric flow rate and divide the square root gravity multiplied by difference in H. So finally, we get our flow coefficients in this experiment.
Conclusion. In conclusion, the experiment meets the Bernoulli's principle, which is a fluid's pressure decreases as its velocity increases and vice versa as its velocity decreases. From the experiment, we can see that as the velocity of the fluid used is increased, the pressure will be decreases.
This is the reference that we use for our experiment. Thank you.